Good evening. Is my voice audible? Good evening, all. Am I audible?
Yes, you are audible.
Yeah. Yeah. Good evening, everyone. Dr. Ganesh Chate here. I welcome you all for the day 4 session number 7 AICTE-ATAL FDP. So it is my pleasure to introduce our distinguished guest speaker, Dr. Ruma Ghosh. Dr. Ruma Ghosh is currently an assistant professor in the Department of Electrical Engineering at Indian Institute of Technology, Dharwad. She has completed her PhD from IIT Kharagpur in the year 2016. Her research interests include development of resistive sensors for 3 different applications: environmental monitoring, health monitoring, and precision agriculture. Her group is also engaged in developing portable biosensors for different cancer biomarkers. She has successfully executed 3 externally funded projects and is currently working on 4 different projects that are funded by SIR, Board of Research in Nuclear Sciences, and DST, and also Indian Council of Agricultural Research. She has 6 Indian patents and has got more than 30 publications in peer-reviewed journals, 2 book chapters, and many conference publications by her name. Madam, we look forward to your session. The platform is now yours.
Yeah. So good evening, all of you. I'll just try to share my entire screen. I think this is the one. Yeah. Is my presentation visible to all of you?
Yes, ma'am, it's visible.
Okay. So thank you, for the Dr. Ganesh for this introduction and for having me here for this talk today. So I think I am the odd woman out here because among the mechanical engineer, probably I am one of the electronics engineer over here. But I would just try to make sure that, of course, you people don't really, find this talk a little insightful and, of course, feel interested to work towards this kind of technologies also after this talk. So my talk is going to be basically on this reduced graphene oxide based resistive sensors for healthcare and environmental monitoring. So if I have to talk about the outline, I will introduce you to the necessity of such kind of sensor development. Why do we have to really kind of, do this environmental work? Okay. And then I'll take you to the reduced graphene oxide based gas sensors that we have developed for basically for environmental monitoring. And then I'll kind of browse you through a couple of works that we have done related to again reduced graphene oxide based sensors for biomolecule sensing. So in biomolecule, you have actually sensed we could sense proteins as well as RNA. So I'm going to talk a little about it, and then I will conclude my talk. So at any point of time, if you have any doubt, I am not able to see right now the Meet interface. So please feel free to talk and then stop me if you have any confusion or any doubt. So just to give you a overview of why exactly this such kind of development is necessary, this is basically a air quality index or the top 10 most polluted cities in the world. This data is of the year 2022. So there is something called air quality index. And if that is standing between, let's say, 0 to 50, as you can see over here, that means it is good to breathe in. If the value comes out to be somewhere less than 100, basically it is moderate, but 100 and above, basically it is very, very unhealthy. Okay. So that is not really the pain point over here. Fine, we have air quality index and, fine that we are measuring our air that we breathe in. The problem point is this fourth and this eighth. Okay. So among this top 10 cities, most polluted cities in the globe, Uh, Delhi stands fourth, and Mumbai also comes close to 100 AQI. So it's moderate. So it's not really very healthy there. Okay. So that's the problem. Now, the question is like, why exactly this should be a problem? Okay, AQI you're talking of. Okay, there is pollution. So why should we really worry about all these things, right? The point is, there are around 3.2 million deaths in the year 2020 alone, which were premature deaths and could be attributed to this pollution. Okay, and how? Basically, and all of these deaths, if you see, there is a pie chart which shows over here that 6% of this 3.2 million deaths was because of lung cancer. Of course, you can always debate that lung cancer, the air pollution is not the only reason. Of course, I agree with you. Okay, there is ischemic heart disease which was contributed to that of air pollution. That contributed to around 32% of this premature death. You have stroke, you have lower respiratory infection, you have chronic obstructive pulmonary disease, COPD. Okay, so these are something which has definitely serious correlation with the air pollution. Okay, so yes, we do have to worry, because it's not only you that you're getting some disease or you're breathing some polluted air. It is also having some terminal outcome, which is definitely not favorable to any one of us, right? So then the point is, if this is already known and I'm giving you a data of 2022, I'm giving you some data of 2020, then doesn't India, or has not our country really waken up and done something? The answer is it has. Okay, so we do have this National Air Quality Monitoring Program, NAQMP, they say, since couple of years. So it's not new at all. It's running since 1990s. Okay, so where they have actually installed, or I think now they could cover till some few hundreds of cities, but we have thousands of cities in the country, and couple of villages as well. I mean, equal number of villages as well. So it is not adequately covering all the cities, number one. Second thing is, if you see, it is actually monitoring some of these pollutants which are like sulfur dioxide, NOx, okay, and particulate matters, right? But then if it is doing already this thing, then why should we really do such kind of research that I'm, trying to show you or will be showing you in a short while, right? So the problem is the monitoring system or the detection system that is employed right now in these air quality monitoring stations. So what they do is they use bulky machines which actually keep taking the air in the proximity for around 24 to 48 hours, depending on what transduction technique they are actually using, and then do the chemical analysis, which takes another 2 days time to give the actual concentration of these pollutants in the air. Okay, and each of these pollutants you are detected using different techniques. So it's not like you are going to get something like GCMS, which is high throughput method, wherein you just enter the sample and get multiple outputs in one shot. It's not like that. Okay, so going by this tedious process, what happens is the monitoring happens only twice a week. Okay, and there have been, I am not showing the data, but there have been data in India itself from Delhi that the pollution or the pollutant concentration changes temporarily, meaning across the time of the day, across different season, okay, across different as I'm saying, like the time of the days, basically this pollutant concentration change. Okay, so in one day the pollutant concentration itself is changing, then monitoring just twice a week is not going to give you the entire picture. Okay, so you may have probably one of these week, which I'm talking of, this twice a week is, let's say, a weekday, a weekend. Okay, when probably there are the office going people are not really traversing themselves. Okay, so this does not really give you the entire picture, and this monitoring is not really adequate. Okay, so this is one way. Second thing is, if you see this particular chart, this is again taken from the WHO's website. It's a global cancer incidence and mortality estimates for the year 2024. Something is there? Okay. So, if you see over here, basically, there are a couple of cancers which are actually, top ranking in this particular list, and it goes for both the genders. So if we talk about male, basically the lung and the prostate cancer leads the list, and if we talk about female, again the lung and the breast cancer basically leads the case. Okay, but this is about the incidence case. About the mortality case, basically, again, so lung and the prostate cancer among the male is the highest, and again in female, basically the lung and the breast are the top rankers among the mortality rates also. Okay, so the point is, if cancer is not new, if cancer is known, okay, so what is it that we can do to really improve this particular data that we are? So okay, incidence has happened, probably incidence is not really in our hand, but can we really somehow improve the survival rates and bring down this mortality rates associated with each of the cancer, right? And this is a global data. I will also show you some of the ICMR data which has been published recently. So this is one of the data which has been taken from the ICMR National Center for Disease Informatics and Research Study. This is an estimation. As you can see, it has also estimated for the year 2025. So the point that I'm trying to kind of make over here is the incidence of cancer is increasing with each passing year in India. In fact, the WHO chief, when we actually could fight over the pandemic, they already told that India should not really worry about the pandemic anymore because they are out of it, but they should start worrying about cancer because this is going to become an endemic very soon. Okay, and if you know, if you really look at the surroundings, you can see that the cancer cases are really increasing in our country. So, of course, incidence is something, as I'm saying, it's a little complex to understand, but we can do something to definitely improve the outcomes or improve the survival rates of the patients. So, in India also, if we see the leading cases in case of male are three leading cases are lung, oral, and prostate. And in case of women, it is breast, cervical, and ovary. Okay, so these things please keep in mind because I'm going to talk about this in a little while. So, fine. Now, the question about this particular cancer is, as I'm saying, the mortality rates, okay, incidence is one thing, mortality rates are also high. Okay, so what could be the reason? So, one of the reasons is late diagnosis of the disease. Okay, and why exactly this disease is diagnosed late? The first thing among our population is lack of awareness. So, we do not do annual checkup, and we also very conveniently wash away some of the mild symptoms which can be the early stage symptoms of cancer also, as nominal infection or cold or whatnot. Okay, and in fact those symptoms are overlapping, that also you cannot do anything. Okay, so there are overlapping symptoms. The symptoms overlap with multiple benign conditions, so that's a problem. Okay, but even though that is the situation, there are, of course, existing clinical methods which are used right now to diagnose cancer. Let us just try to understand what are the problems associated with it. Okay, so the first thing is sophisticated instruments. Okay, so take any cancer, basically it will be like you'll have some scans which will require like some lab intensive instrument. You have biopsy, it will, in most of the cases it will require surgical intervention followed by imaging. Okay, so you require sophisticated instruments. Sample preparation is required for most of the diagnosis. So if you take biopsy, of course, a TDS sample preparation is required. Similar for any kind of any spectroscopic method, right? So sample preparations are required. The moment sample preparation comes, you also require expertise, skilled expertise to do the sample preparation and run the machine, right? Okay, and of course, they analyze the results, right? So based on that, only the clinician, the final doctor, is going to take a call and clinical decision that what is the disease and how should we move ahead about it, right? Fourth thing is lab intensive. As I said, most of these methods are actually lab intensive, so it cannot really be, the existing methods cannot really be translated to a take home solution. So that's one thing. And of course, these tests, some of the tests are really, really expensive. Okay, so now the point is, how do I really solve our situation in this case? Okay, one, because we have a, when, even if you ask me if I am observing some mild symptoms somewhere, okay, my tendency will be to just kind of suppress that by taking some of the medicines which are readily available in our country, or probably go to a general physician, take some kind of medicines which will suppress the symptoms and just get well. Okay, so there is a huge resistance for me to go and take this complex test, right? So this can only be solved if such kind of diagnosis or at least some preliminary testing about the cancer or any terminal disease for that matter can be brought home like a glucometer, okay, and it should be accurate and efficient, right? So that is one of the thing that one can really think of and contribute to, right? So, how can you do that? In order to do that, first thing to be done is you have to identify the specific markers for the disease, not for only cancer. Of course, I'm going to talk about cancer, but it's true for any disease. And you have to develop portable sensor because you have to carry it. Like it should be something which you can take home, which is like bedside solution, right? So these are the two things that has to be done in order to really improve the situation. Specifically in case of cancers like lung cancer, whose diagnosis mostly happen only at advanced stages, and there is absolutely nothing we can do until we have something like this which is portable and the patients can really take the test at home, okay. Now the question is, these all are fine. Now, why are we listening to this? Is this really something wherein I'm going to really do the pep talk? Answer is of course no. I'm going to really propose some technical solutions to some of these problems. And the way I have kind of spun around my talk is, I will keep giving you solutions and I will also keep indicating the problems in each of the solution that we have developed. Okay. So that is where I'll just try to kind of imbibe in you, give you an impression that how research is a continuous process and how after long years of research only, one thing can really be translated to certain product which can go to the end users. So that is why all of your interest and help is required in a focused way. Okay. So first starting, now, graphene, I think many of you are aware of this graphene, the properties, different properties of graphene. Mechanically, if I talk about, it is harder than tin or even diamond. It's the strength is very high, tensile strength is very high. Okay, and if I talk about electronically, so graphene is having zero band gap. Pure graphene has zero band gap. Uh, it has very high number of charge carriers and the mobility of the charge carriers is also very high. So that means the conductivity of the graphene is going to be finally very high. But if you are designing any electronic device, if you have a material which is having, let's say, zero band gap, many of the times this does not really come to use. Okay, it's a problem. It's less than a property or less than a advantage, more than a problem. Okay, so in kind of in a quest to really sort that problem out, people have tried a lot of things including graphene ribbons, and a lot of other things. But one of the sustainable thing that has sustained all these years is not having graphene but having reduced graphene oxide. Okay, so you formulate, you extrapolate, you exfoliate this graphene sheet from a graphite powder. Okay, but in the process you will get this oxidized on its basal planes and at the edges, and then you reduce down these functional groups judiciously. Okay, do not try to reduce it completely, it's not possible also, but it is not our intention also, because if you really reduce down all the functional groups from graphene oxide, you will get what is called graphene again. So that is what we do not want. We want to engineer the band gap, and trust me, depending on the reduction extent, you can engineer the band gap of the this reduced graphene oxide also. Okay. Now, as you know, graphene is a 2D carbon nanomaterial. Basically, it has a very high surface area. Okay, and that actually acts a very excellent property which is required for the gas sensors, right? So with this in mind, we started our research, and I will show you some of the results which are also reported in the literature. So this is the response of the graphene. We have actually worked with graphene which was coated on some solid substrate and interdigitated electrode. We also worked with graphene which is like kind of coated just on a filter paper, okay, lab filter paper. So it's flexible that way, right? So what we did was we actually tried to test this reduced graphene oxide for ammonia, which is also another environmental pollutant. So if you can see, the major advantage of graphene is it gives response at room temperature. Okay, and you must be asking why exactly room temperature sensing is so hyped up. Okay, the answer is, if you have to give higher temperature to your sensor, the power consumption increases. Okay. And not only that, if you really want to make this devices portable, the packaging material, okay, again, I'm talking, I think, predominantly to the mechanical engineers. Basically, you know that you have to have some temperature coefficient for each of the insulator, and that has to really sustain this kind of temperature, which we are going to, which we have to probably emulate across the sensor. Okay, so there is additional amount of work and resources which are required if your sensors are operating at higher temperature, right? So that graphene solves, because it does not require high temperature. It can do, or it can sense gases only at room temperature. Okay. So we, as I'm saying, we tried this non-flexible and as well as flexible substrate graphene, and we found that we could actually get sensitivity of a response of around 5% to around 24% for 200 to 200 2800 ppm of ammonia. In case of flexible graphene, the response was a little higher, and that is like from 400 to 4000 ppm, we got a response of around 5 to around 60%. Okay. We also got exposed this graphene to humidity. Okay. Humidity sensors are always everywhere required, right? For different kind of experiments. So here we exposed this graphene to 10% to around 100% of RH, and we got good response there also, from around 4.7 percentage to around 19%, 20%. Okay, and this is another paper which has been reported. I mean, this is not something which we have done, wherein graphene is reported to sense NO2, nitrogen oxide, that is a serial pollutant, right? Now, if I talk about the sensing mechanism over here, what you have, as I told you, RGO basically has this different functional groups like COH, OH, C double bond O at its edges and on the basal planes. Okay, so these are, and along with that we have sp2 hybridized carbons also. So these atoms, all these actually acts as an adsorption site for the gas molecules. They come and interact with these sites, get adsorbed, either physisorbed or chemisorbed, and which leads to the electronic exchanges between the gas molecule and the RGO, and the resistance of the RGO changes. Okay, so it's fairly simple. Now, before I move on to any next thing, I would like to like the audience to pay an attention, because after this slide I will have questions, and until I get the answer I will not move ahead. Okay, so I showed you this thing, right? That we have just developed this RGO based gas sensors, and there are literature which are reporting this sensors on NO2 as well. Now, before moving ahead, I will just cite out or list out some of the parameters which are very important related to any gas sensor. Okay, doesn't matter it's resistive sensor. In our case, resistance change, so it's a resistive sensor. But for any sensor, these parameters are important, right? So what are those? Let's say, as I showed you in the previous slide also, this is typically what a dynamic response of any sensing layer, resistive sensing layer, looks like to a particular gas. So different concentrations of a particular gas, this is how the cycle is going to look like, right? So let's try to define each of the parameters. So response, if I say, response is basically how much the resistance in this case changes due to the exposure to the gases. Okay, so now this response can be calculated as delta R by R. So here I have written as delta R, resistance of the gas, minus the calibration resistance, that is the baseline resistance, which is here, okay, before exposing the gas, right? This is the baseline resistance, divided by that baseline resistance into 100. Okay, this can go other way also. It can be R calibration minus R gas divided by R cal, depending on whether the resistance is increasing due to the exposure of the gas or the resistance is decreasing, right? So this I can change, right? So in all, the response will be delta R by R calibration. Okay, this is one way. Another way is R calibration by R gas. So R calibration is the resistance, this baseline resistance, and R gas is basically this resistance which you are getting in presence of the gas, right? This formula also can be reverse way, depending on if the resistance decreases, basically it will be R gas by R cal, right? Okay. Now, in what all two cases, basically these two formulas have to be used. I mean, which one to use? So first thing is, if the response is relatively small, okay, so it's not really changing much. So let's say from 1 kilo ohm, it's just going to 1.3 kilo ohms. Okay, not more than that. So that kind of condition, you'll use this percentage formula. Okay. Now there are cases where the resistance go very high. The change is very high with exposure to the gas. In that case, this percentage formula is deceptive. Okay, it's deceiving, right? So there you use this normalized resistance formula to calculate the response. Okay. So this is how the response of any resistive sensor or any sensor, they will have different parameters, is defined. Now, what is selectivity? Selectivity is, let's say you have developed a sensor and you want to develop this sensor only for a particular analyte. Okay. It may be pressure also for that matter, right? But then if it is kind of, developed for sensing a particular thing, either chemical or physical, then it should be just sensitive towards that particular parameter. Okay. So it should not really be like in terms of gas sensor, if I talk about. So it should not be the case that you have mounted a sensor in this room and then it is responding to humidity. It is also responding to, let's say, NOx. It is also responding to any other gas as well as temperature. Okay. So that makes the selectivity of the sensor very poor, right? Okay. Now coming to the response time. So response time is the time taken by the sensor to respond, reach 90% of the steady state of its response. So this is the steady state, right? In each case, this is the steady state, right? Okay. So the time which the sensor has taken, let's say from here to reach 90% of its response, that is called response time. Okay. Similarly, recovery time is the time which is taken by the sensor to recover to 10% of its baseline. Let's say this was your baseline. Okay. So till 10% of its baseline, how long did it take? Okay. Because usually what happens is otherwise in here, this resistance usually saturates, and here it is an exponential decay. Okay. So what happens is if you just take the entire time, basically it is many a times deceptive. Okay. So you don't get to fix or tap that time only. That is why this 10% and 90% figure has come. Okay. So it's basically these two parameters, response time and recovery time, tells you the speed of the sensor. Okay. How fast the sensor responds or recovers. Next is the repeatability. So let's say in here, what I have done is we have exposed the sensor to multiple different concentration of the same gas. Okay. Now, what if I would have exposed this sensor to the same concentration of the gas multiple times? Let's say 5 times, 10 times, 100 times. Okay. So my desired output is, let's say if the response is here 40%, even if it goes to 100 times, it should be 40% only. Okay. So if that is the case, I say that it is heavily or highly reproducible. Okay. Highly repeatable, right? Now coming to reproducibility. So let's say you have done a lot of excellent job. You have spent 15 years to optimize the device. Now it is ready to be translated. So what you have to do is you have to produce this sensor in bulk amount, right? Bulk numbers, right? So if you are doing this, what you have to do is you have to also see the device to device variation. So I have kind of, fabricated, let's say, thousands of sensors. Each of these sensors should have this similar signature to same concentration of the gas. Okay. So that is what is called the reproducibility. What is my device to device variation? Okay. And lifetime is lifetime, for how long it stays alive. Okay. For how long, let's say I have developed this sensor, I have kept it in the shelf. Okay. I've stored it. So for how long can I really keep it storing? And after what I should discard it and get a new sensor. So this is what is the lifetime, right? So having said that, I will go back to my previous slide here. Can someone from the audience tell me that what are the problems you see in this particular slide in the context, in the parameters that I just discussed right now? Someone has to read it out because I'm not able to see my Google Meet with this presentation on. Yes? Or should I really just...
Yeah. Uh, should we remove the restriction, madam?
No, no,
From the,
that's okay. That's okay. That's okay. 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 There is something like, yes, sir. Yeah. Did you get my question? I'm asking that I just uh, listed all these parameters. Now, if I talk about, take you back to this slide, in this slide, what are the problems that you see? Is there any problem in the RGO based sensors? Now I can see the chat also, so if someone can write. Does any other functional groups affect the properties of the sensor? No, that's okay. I'll come to this question and answer this question in a little while. But just look at these sensors. Let's not talk about the sensing response right now. So I said that we have developed a RGO-based sensor, and I have given you the parameters on which the sensor figure of merit is evaluated. Now, looking at this sensor response, can you see or do you feel there is some problem? Anyone?
The graph shows like with respect to time, the response intensity is changing.
That is supposed to happen because it is increasing concentration. So, with increase in concentration of the gas, the response is supposed to increase. It's not audible to me. Okay. So if you see over here, I have talked about selectivity, right? One sensor should be sensitive towards just one gas. Here itself, I have showed you three things. One is ammonia, one is humidity, another is NO2. Okay. So the moment you mount a RGO-based gas sensor in any of the room, if the resistance changes, you do not know what it is changing for. It is because of humidity, it is because of ammonia, or is it because of NO2? Right? So RGO has a poor selectivity. That's first point. Okay. Second thing, if you see, this is to the scale. Please pay your attention to the x-axis. Okay. So the x-axis for just merely 5 or 6 or 7 concentration of the gases, this is running till 12,000 seconds. Okay. So even though I have not projected on the screen what is the response time and recovery time of the sensor, you could make it out from this overall scale that the response time and recovery time are quite long, right? So it is slow. Another problem which I have not listed in the parameters, but you can see if her device has to be repeatable. I spoke about repeatability, right? Then each time the gas is desorbed from the sensor, the resistance of the sensor should reach this baseline itself. Should reach to this zero, right? But look at this, it is over recovering, it is going till negative. In the second graph, it is moving up. So this is something in technological term, it is called as baseline drift. Okay, so your baseline is drifting. So even if your sensor is very repeatable, basically because of this drift, your microcontroller, which you would have kind of programmed to evaluate the sensor response, might not really be able to take it as a repeatable sensor because your baseline was stamped at some value like here, but with each passing cycle the baseline is shifting, which this information we have not passed on to our microcontroller. Okay, so these are the problems that were there in the intrinsic RGO. Just to kind of reiterate, what are the challenges? Longer response time and recovery time, so the sensor was slow. Poor selectivity because it was able to sense multiple gases. Baseline drift was an issue, and poor response. So response was also not that great. If I really show you in here, this response to 2800 ppm is just nearly 23-24%. Okay, so not that great, right? And in environment, the concentration of ammonia is in ppbs. Okay, so this sensor is not going to be able to sense a ppb level of ammonia at all, right? So it will be the NO2's case, right? So these are the problems, right? So then the question again comes, how to solve these issues, right? So how do we solve these issues? One of the way, of course, this is one of the ways, is to functionalize. That is, you attach something more to the RGO so that you get some improvement in the sensitivity or in the sensing performance. Okay. So we did it multiple ways. I will just kind of cite here two of the functionalization that we have done. The first functionalization is RGO and tin oxide, SNO2. SNO2 is known to be a very popular and widely used metal oxide, which is in the commercial lines of resistive and electrochemical sensors. So most of these Taguchi sensors are based on this SNO2 material only. Okay. So what we did, we synthesized this SNO2 nanoparticles and we formed a composite with RGO and SNO2. Okay. So what we got, see, earlier the response was in terms of percentages, right? Here the response is in terms of times. So the resistance change is huge, right? So even though because of our experimental, limitation, we could not really test it below 400 ppm. 200 ppm was also a problem. But here we can see for 400 ppm itself, the response is close to that of 3 times. So if the resistance, baseline resistance to start with was 1 kilo ohm, it has increased to 3 kilo ohm now, right? So of course, if I extrapolate it, I will be probably able to, if not more, at least be able to detect hundreds of ppbs of the gas, right? This is also ammonia, by the way, right? So here, this particular graph tells you or gives you the overall a picture of multiple kind of material, starting from intrinsic RGO to intrinsic SNO2. Okay. And in between, we have different composites, different proportion, mixture of this RGO and SNO2 in different ratios, weight ratios. Okay. And we found out that 10:8. So 10 is your RGO, 8 is your SNO2, is the ratio where you get the best or the highest response, and that too at room temperature. Okay. So RGO senses gas at room temperature. SNO2 sensors could sense gas at this ammonia at 200 degrees Celsius. Okay. We did the in situ synthesis of hydrothermal synthesis of RGO and SNO2. That could also sense gases only at 120 degrees Celsius, not lower than that. But remaining of these basically could sense at I would say room temperature, but the sensitivity or the response was highest in case of 10 to the power 8. Okay. And not only the sensing, so see, this sensing, this response is not only higher than that of intrinsic RGO, it is also better than that of intrinsic SNO2. SNO2 is very highly sensitive. Okay. So we did something, there was a synergistic effect because of which the composite response was even higher than any of the intrinsic material, right? And not only the response, even if you talk about, there is a plot of recovery time over here in seconds. So if I take you to only RGO, okay, so RGO is probably not over here. If you talk about this SNO2, metal oxides are supposed to be very, very fast. Okay. So if you see this blue line, which corresponds to 10:8 composite of RGO and SNO2, and this purple line or pink line, which corresponds to SNO2, intrinsic SNO2, you will see that these two lines are very close to each other. Okay. So not only the response of the composite was better than that of intrinsic SNO2, but also the recovery time was as fast as that of intrinsic metal oxide, right? So this is what we could get in this research, right? And of course, the reason was because this SNO2 is an N-type material, and the RGO is a P-type material. So there are multiple types of adsorption sites. So remember, in case of RGO, I said that there are functional groups which are present over there, which behaves as an adsorption site. Okay. In addition to that, you have metal oxides, depleted metal oxides, which are actually the adsorption sites for the gases. Also, this metal oxide and the RGO, which are forming junctions, PN junctions. Okay, so this is a third type of adsorption site which is available in this composite, which was not available in either intrinsic RGO or intrinsic SNO2. So that is why the response was very, very high as compared to that of the intrinsic material, right? So the salient features here were, we got enhanced response, we got shorter recovery time, and we also got better selectivity. These were not sensing humidity at all. We could not test it for NO2, but we tested it for other gases also. I have not, in the interest of time, I have not added the results, but it had the better selectivity as compared to that of the intrinsic materials as well, right? So now this is not the only power of functionalization. So what did we do? We mixed RGO and SNO2 and we got the sensing, right? What if you use some different material to functionalize RGO? In this case, we have used platinum to functionalize. So we had platinum salt. We just mixed that platinum salt along with the RGO solution and we reduced it. Okay. So RGO also can be chemically reduced using sodium borohydride. the platinum salt also could be reduced using sodium borohydride. So you just use sodium borohydride and reduce both of them together, right? So we did this STEM imaging, and you can see the graphene or the RGO, and it is having this platinum decoration on top of that. Okay, so this is a very nice, I would say, SAD pattern of the material. Some questions there? Should I check? Oh, let's. Yeah, so I think Siddharama Adi has asked this question, that does functional groups affect the properties of the sensor? We are precisely talking of this only right now. And I think somebody tried to answer the question, low selectivity. Yes, it is poor selectivity. That's correct. You're right. Is there any question? Yes, Dr. Badigar, you have a question. Dr. Shankar? Probably you are on mute. You have to unmute yourself. No? Okay, I'll continue. If you have any question, you can put it on the chat box. I'll keep looking at it in a certain frequency. Okay, so this was an RGO platinum, I would say, composite. And then what we did was we tested it for multiple other gases. So here, see, we were testing RGO with ammonia so far. So here also we have tested it for n number of gases, and we found that since the functionalization is now of different material, basically the selectivity also shifted. Okay, now from ammonia it has started, because platinum is a catalyst and it is known to sense hydrogen very nicely, and we could see that change in the sensitivity of the RGO platinum composite also. So functionalization does not only help you to improve the sensing performance, it can also help you in modulating the selectivity of the sensing layer, okay, base sensing layer. So we did all these kind of thorough characterizations, and what we got was response and recovery times were of few hundreds of seconds. And of course, we explained the sensing mechanism also. I'm not going into the details of it. If you have any questions, you can ask. So far, is everything clear? Or if you have any questions, we will ask, because I'm going to now change from gas sensor to the biomolecule sensor. I would like to have questions if you have anything related to the gas sensors. Okay. So any questions so far? Things were okay?
Yes, ma'am. Yes.
Okay, great. So fine. So with this, so far, what we have done is I just kind of explained you the RGO-based gas sensors. Now I'll move on to some biosensors. The first biosensor is basically for a protein. So what we have done is we have come up with a very novel and very simple device structure. Here also, if you see this black portion at the center is actually RGO, and on it is decorated with some immobilization agent. Okay, so in any biosensor, there are three important things. One is transducer layer, which in this case, our surface modified RGO is playing the role. You have bioreceptors. So depending on what is it that you want to sense, you have receiving unit, which are very, very specific to your target, right? So in case of proteins, it is monoclonal antibodies. In case of RNAs, it will be single-stranded DNAs, and so on and so forth, right? So in this case, basically, I'm going to first talk about the protein sensors. So in here, we have this monoclonal antibodies, and then which is actually very selectively binding with these antigens, right? So we developed the sensors, we characterized this using, let's say, AFM. So here, what we could see is this is the AFM image of only graphene, or graphene oxide rather. Okay, so the thickness varied like from 0 to 2. So average thickness was around 2 nanometers, right? But when we actually coated the antibodies, so it was in this particular case, it was RGO was surface modified using gold nanoparticles. Okay, so on top of that, we had these antibodies, right? Now the antibodies are like Y-shape, as it has been schematically shown, and usually these regions are known as FAB regions, that two antennas, which are specific to the antigens, and the Y region, the anchor region, is known as FC region. Okay. Now, these two antennas are the bioreactive or bioactive regions. So we need to preserve those, right? So our intention will be to just kind of, anchor the antibodies like this, correct? But when we did the AFM image, we got that it's like this, okay? So you could see that there are thread-like structures, okay? So if it was like sitting like this, you could have seen just two heads, nothing else from the AFM, right? But here you could see thread-like structures. So basically they were sleeping like this, right? So anyways, this we got to know later, but before that only we have characterized. So what we did SEM imaging also. So in this case, SEM imaging, you can't really get to see whether it is standing like this or it is kind of, lying down there, like this. So we tested this particular sensor for two of the cancer antigens, which are common. So this CEA is common across multiple cancers, which is good as well as bad. And this CIFRA 21.1 is also expressed in case of multiple cancers, but specifically we wanted to do it for oral and lung. So now, why am I saying that if it is expressed in multiple cancers is, if you are developing sensors for these two proteins, using it for cancer diagnosis, let's say someone is taking it home and doing the test for CEA and CIFRA and finds the value to be higher than the threshold, okay? The problem is the person will not get to know what kind of cancer he or she is suffering from. Is it oral cancer? Is it a lung cancer? Is it a colorectal cancer? What is it? Okay, so that's a problem. So what? The patient should go and get the full body checkup done? That's not done, right? Also, the CEA specifically is an inflammatory marker, which is overexpressed not only in terms of cancer, but also if you have nominal cold or some infection going on in your body, then also this concentration is going to be high. Okay. So that is where basically we learned it in a very hard way, but we learned that these two probably are not really good markers to work with. Okay. But we learned after doing a lot of work. So in this case, what happened was, like I said, in case of RGO, which was modified with gold nanoparticles, the antibodies were kind of lying down. They were not upright. Okay. So what our kind of observation was that this particular FC region is having some chemical bonds like, chemical organic groups like COH or COO, something like that, right? So I, in collaboration with one of the faculty members from chemistry here, he designed some of the polymers which are rich in nitrogen. Okay, so COH, CO, basic chemistry, they have very strong covalent bonding with the nitrogen atoms, right? So they have come up with multiple polymers, and we could see that, yes, the response was quite kind of enhancing. When we used, instead of gold nanoparticles, this red here are actually the polymers. So we could get really very good sensing with these polymers. And we did the AFM characterization also, not shown over here, and we could see the beads only, the tops only. They were not sleeping like this, right? But then, if that is the case, what we did, as I kind of told you already, that CEA and CIFRA are not really good markers to work with. We started working with a clinical marker, which is CA125, which is a clinical marker of ovarian cancer, right? Now here there is an issue, and what is the issue? If you see, for the same structure where we were functional, surface modifying this RGO using the polymer, and then instead of the monoclonal antibodies of CEA or CIFRA, we were using the monoclonal antibodies of CA125, right? If you see the response of this sensor to 1 nanogram per ml, to 5 nanogram per ml, to 20 nanogram per ml are overlapping. Okay. In fact, 20 nanogram per ml and 50 nanogram per ml also, if you see this error bar, basically they are overlapping. Okay. So the moment the response is anything between 20 to, let's say, 40, it is very difficult for you to tell whether it is 1 nanogram per ml of CA125 or 50 nanogram per ml of CA125. Okay. So resolution of the sensor, we were not able to get, right? So we did a lot of experiments. We did with gold nanoparticles, we did it with different kind of, such kind of networks. We could not figure out what is going wrong. So then, defeated by everything, what we did was, we just simply tried to immobilize these antibodies on RGO itself. Okay. So RGO, as I showed you already, it is having this C double bond O, COOH and hydroxyl groups, right? So now what does this signify? This signify that not all FC region is terminated with COOH or C double bond O, right? It's not. Like in case of CEA or Cypher 21, they were. That is why they were anchoring nicely. But in CA125 case, probably the FC region is itself rich with nitrogen, okay? So if it is having nitrogen and if we are giving it a polymer which is also having nitrogen, they will repel each other, right? So that is what was happening in case of polymer functionalized RGO. But RGO having this carboxyl carbonyl group, they could actually anchor this nitrogen rich FC region of CA125 very nicely. Okay, so we did a lot of characterization. Like I said, you see this AFM image, like, so we are not able to see such kind of sleeping or lying down antibodies. You could see this strong two heads from the top because AFM scans like this, so you could see just two heads from the top, right? So you could see this bright spots of the antibodies FAB region, right? So we were confirmed that it is actually sitting upright on only RGO, and that's where we went ahead and did the characterization of all the sensing, sensor related tests. So here we could actually test it from 1 picogram per ml to around 300 nanogram per ml. The threshold of CA125 is 35 units per ml, which translates to 200 nanogram per ml. So that is why we had to test it till 300, so that we could see that if we can differentiate between the threshold, the healthy and the unhealthy region or not. And also we tested this sensor using some of the patient samples. So we actually collaborated with KIMS Hubli over here, and we collected some 9 patient serum samples who actually reported in the OBG department for potential ovarian tumors, not necessarily cancers. And we tested the serum with our sensors, as well as we tested these serum samples with the standard ELISA kit of CA125, which is a clinically used method. And as you could see, the responses are almost same of that what we have observed with our sensor. So this was a very strong cross validation that our sensor is working fine. Okay, so this is one of the work that we have done. The second kind of biosensor work that we do is in terms of RNA. So PCA3 is an RNA which is expressed in case of prostate cancer. Okay, now prostate cancer, in case of ovarian cancer, what did I say? CA125 is the clinical. So if anyone is expressing any symptoms which is related to that of ovarian cancer, the doctor will first prescribe the CA125 test. Okay. In case of prostate cancer, if somebody is showing some symptoms which are overlapping with that of prostate cancer, they will prescribe PSA test. Okay. But the problem with PSA is that it is not specific to prostate cancer. It can be high, the levels can be high. The threshold value is 4 nanogram per ml there, but it can be high because of unrelated reason. Okay, it can be a benign prostate hyperplasia, it can be UTI also. Okay, so it's not very specific. So because of which, what happens is around 50% of the prostate biopsies are getting done unnecessarily because we do not have a better marker. Okay. So with advent of this bioinformatics and we now this biology I would say community, they have agreed that whatever tests they do on patient, those all data will be made public. Okay, invariably public, right? And until you do so, you'll not be able to publish the paper. That's what is the mandate. So you have a huge set of data now coming up in the public domain, right? So from there, people could find out that this PCA3 RNA is one thing which is really very, very specific to prostate cancer. Okay, so it is not expressed in case of benign cases at all, right? So if that is the case, then we started and PCA3 is an RNA, and we all know from COVID times that if it is an RNA, it is to be tested using PCR. Okay, but again, PCR is a lab-based method, right? So again, my early diagnosis is getting hindered there, right? So what we did was we tried out to develop this resistive sensors, which is again having this RGO. To start with, we functionalize it with again gold nanoparticles. And in this case, it is not the antibodies, but it is basically the single-stranded RNAs, DNAs, which are complementary to that of the gene sequence of PCA3 RNA. Okay, so you have for every DNA or RNA, you have this 80 DG, GC sequencing, right? So you have a complementary sequence of the PCA3 RNA and you use it as a probe, okay, or bioreceptor, right? So that's what we used. And then we kind of introduced different concentration of your PCA3 RNA, and we found that the resistance is indeed changing, right? So with this kind of work, what happened was, of course, we did a lot of characterization. We did the AFM also. Here in AFM, we could see very nice heads of the probes. Okay, so these are the bead-like structures of the probes, and then after the the RNA DNA hybridization happens, then also you can see this very nice beads, right? So when we then, of course, went ahead with different characterizations of the RNA of the sensors. So in here, if you see, as I showed you for CA125, the antibodies could be actually anchored directly on top of RGO. Okay. Now here also the confusion comes that couldn't it be the case with this ssDNA also? So what did we do? We varied the volume of the 5 nanometer gold nanoparticles across the devices, multiple devices for each of the concentration. So first device here you see is 0. That means we have tried to develop the sensor along with only RGO and no gold nanoparticles. Okay. So if you see over here, basically the response is very low. Okay, almost nil, right? But when we gave just 5 microliters of gold nanoparticles, basically you get a very good response, and these responses are for 50 nanogram per ml of the PCA3 RNA. Okay, we did a lot of optimization. So the first optimization was done for the concentration of the probe. Then the optimization was done for the incubation temperature and duration. We found out a lot of parameters from there, because this is the first time that we were developing such kind of devices. These optimizations were necessary. And then comes the surprise. So after doing all these optimizations, we finally went ahead and tried to characterize the sensor for different concentration of PCA3, right? So this F shows that image. Now in this, if you see, there is a problem. Please follow the pink bars, okay? So the pink bars are the sensors which are fabricated using 5 microliters of gold nanoparticle and PCA3 9 nanogram per ml, the probe here. Because after 9 nanogram per ml, we saw almost the response was saturating. So we were like, okay, higher the concentration of the probe, that means we are using the probe more. Let's use it as 9 only, right? So the problem, if you see over here, from 1 pico to 10 to 50, it was okay. As the concentration increases, the response of the sensor should increase. Very nice. But when we actually fabricated 3 devices and tested it with 100 nanogram per ml of PCA3 RNA, we saw that the response was not increasing any further. So it was saturated. Okay. So the simple, one of the reason that we could kind of, think of at that time was probably, even though in here and in here, it turned out that if we use just 5 microliter of gold nanoparticles and 9 nanogram per ml of the probe, probably it is sufficient enough for developing the entire sensor, but that may not really be the case. Okay. So what we did, we used a larger volume of gold nanoparticles and higher concentration of the probe, and then did the test. So here is the interesting result. So now if you follow the maroon line, so in this maroon line, you can see that the response is almost comparable to that of the pink line itself, except for this 50, between 50 and 100. Okay. So 100 nanogram per ml, the response increased as it was supposed to happen. Okay. In this higher concentration of the probe. So this particularly gave us a confidence that yes, with 5 microliter of gold nanoparticle and 9 nanogram per ml of the probe concentration, it was not sufficient enough to anchor the 100 nanogram per ml of the target. Okay, so this also had to be really figured out, right? After that, of course, PCA3 is another advantage of PCA3 is it's an urinary marker. Okay, so if it's a urinary marker, that means it comes in the urine, right? So if it's a urine, it comes in the urine, and we are trying to develop resistive sensor. It is highly saline in nature. So urine is a saline solution, right? So we really need to understand whether this salt present in the urine is going to really change the resistance of the sensor or not. Okay, because it is supposed to be, expected to be, right? So what we did was, we tested the sensor with this phosphate buffer saline solution. This is a standard saline solution, okay? And we got almost no response. We developed the confidence, and then we went ahead and extracted the RNA mixture, the complete RNA, myriad of RNA from different cancer cell lines. Okay, so like this T47D is the breast cancer cell line, A549 is the lung cancer cell line, and this is the negative control, and LN cap is the prostate cancer cell line. Okay, so as you can see over here, basically the sensor responded only for the LN cap line and did not really show any significant response for anything other, right? And this was actually cross-validated using the PCR results. As you can see over here, neither T47 nor A549 expresses PCA3. It's only LN cap which overexpresses PCA3. Okay, so that is what we also got, right? So this was the confidence that we developed, but this was a problem that, of course, it is having a very, so in this case, we have to use a very huge amount of probe in order to get some good linearity of the response of the sensor, right? So we were like, okay, let's change this. Let's try to see if we can do something else. So what we did, we again here kind of, changed gold nanoparticle to something called glutaraldehyde. Glutaraldehyde is an aldehyde, and which has, so these probes have amine termination. So amine group has a very strong relationship or strong bonding. They can form strong bonding with aldehydes. Okay, so that's the only change that we did in the device, and we characterize our devices. If you see, of course, we have done the material characterization, SEM, EDS, UV visible also. It's not shown over here, and then we exposed this RGA-GA sensor to PCA3. And as you can see, we could test it from 0.1 nanogram per ml to 100 nanogram per ml over here. And we could get very nice increment in the concentration with just 9 nanogram per ml of the probe. Okay, so earlier it had to go till 500 nanogram per ml. Here, with just mere 9 nanogram per ml of the probe, we could actually get very nice concentration, very nice response for all the concentration of the PCA3. So then that developed a lot of confidence in us. We did all this selectivity test over here. This is nothing new from the previous thing. Only one point that I would like to point out here is please pay attention to this two cell lines, that is PC3 and DU145. These two are also prostate cancer cell lines. Okay, and these two lines do not express PCA3. Okay, only LN cap expresses the PCA3, and this is also clear from this PCR result. So it's only LN cap where you get this, dark shade. DU145 nothing, PCA3 no band, T47 and A49 anyways they are breast cancer and lung cancer cell line. They are not supposed to express PCA3, right? So in this PC3 DU145, despite being the prostate cancer cell line, they do not express PCA3 RNA. And the same thing we got with our sensor results also. Okay, so we could only get the response only for LN cap and for no other cell line RNAs extracted from no other cell lines, right? So then we went ahead and then did the test with the real-time sample. We collected, so we are working in, this is a project in collaboration with KLS Belgavi, the hospital. So we have two clinicians from there. So we got 2 urine samples from there. We collected it and we tested our sensor with the urine samples. We got good response, and these are confirmed prostate cancer cases, by the way. Okay, so these are expressing PCA3 over here, and we also cross-validated our response with the PCR results. And as you can see urine sample 1 is here, urine sample 2 is here. Here, if you repeat, both of them are expressing PCA3. So this gave us confidence that yes, basically we are on the right path. So resistive sensors, it is very easy to develop the interfacing electronics. Okay, so if we can really bring up in fact, we developed the interfacing electronics for the CM125 sensor also. So it could be made portable. So it's just something which can be taken home or taken anywhere. Okay, so that is why resistive sensor is best, and why, despite being the fact that PCR is so sensitive, despite being the fact that ECLIA ELISA exists, these resistive sensors are finding their own way of interest in the research community. Okay, so with this, I would like to conclude my talk. I have discussed about the RGO-based sensors for environmental pollutants like ammonia. I have discussed how do we enhance the sensor performance by functionalizing the RGO, and not only the enhancement of the sensor performance, but also the selectivity could be modulated as I showed it. I have also showed that rapid label-free, easy-to-use resistive sensors could be developed for a few protein, which are biomarkers of a couple of cancers. And I showed you how residue sensors were developed for PCA3, which is a specific better marker for prostate cancer. So with this, I would like to thank the funding agencies who have been funding our research. And these are my students who are the, front runner of all this entire group. I mean, all this work, they are the working hands, the collaborators and the organizing team of this ATAL FDP. So thank you so much. I would be happy to take questions if there are any.
Yeah, thank you, ma'am. I request participants to ask any questions or any doubts if you have. Class is open for all.
You can also put your questions in the chat box. By the time participants ask, I have a few questions from my side, madam.
Yes, please.
This is Professor Vinayak Malik from organizing team.
Yes, Professor Manu. Please tell me.
I was in touch with you from past few days.
Correct.
So my question is with respect to materials. Now, do you make your own graphene?
Yes.
You buy it, outsource it from outside?
So as long as reduced graphene oxide is concerned, basically we make it. We synthesize the reduced graphene oxide. So basically we synthesize this graphene oxide using Hummus method, and then on we reduce it. And for some of the work, we also have started working with CVD graphene. So those we do have few furnace with us, but we have not started optimizing the parameters for CVD growth of the graphene. So we purchase it. But as far as RGO is concerned, we synthesize it.
So what's the yield that you're getting?
Oh, that is a difficult question because we do use something like 3 gram of graphite powder. And usually for our kind of applications, we do not want agglomeration of the graphene sheets at all. So finally, what we get after the Hummus method is complete is GO, which is dispersed in the DI water. So if we want to really find out the yield, we have to form powder from there. So we have to evaporate the entire DI water and form the powder. But that leads to agglomeration of graphene over there. So we don't do it. We let it stay in the dispersion form only. So I will not be able to give you the exact value of yield in that case.
Continuation of this, there are like sol gel methods and other chemistry-based reduction-based methods.
Correct.
So similarly, like since microwave is one of the subtopics for this FDP, so any inputs or any points from your side, like how like microwave is connected in manufacturing of graphene or graphene?
Yes. I can't say that only graphene. I'm not updated that way. But as I'm saying that graphene functionalization is a very huge topic even now. Though people are trying to work with this 2D transition metal dichalcogenides, MXenes are coming up these days, boron nitrides are there. So, but still, this functionalization of graphene, there are lots of work which are done with microwave assisted hydrothermal method or microwave assisted methods. In fact, the work that I showed you for RGO SNO2, it was actually synthesized using this microwave assisted hydrothermal method only. So yes, microwave is a huge thing. And in fact, to add to that, I didn't add these results here because in the interest of time, there is something called absorption of microwave rays. So what you have is if you do some communication, so let's say if some aircraft is kind of flying and it has gone to some warfare, basically you would like the certain wavelength of the microwave not to penetrate inside the aircraft. Okay. So this requires absorption of the microwave rays, right? So this RGO we have tested during my PhD days behaves as a very good absorption material in microwave. Okay, so if anybody is actually interested in working in that area, basically this is one of the area one should take forward. My only concern that I could not pursue it with because my interest was in something else Another thing is if you really want to coat the windows with graphene, the thickness of graphene that I was using, it was opaque. Okay, so that is not something which one want. So they want to keep the windows transparent as well as get the absorption properties, microwave absorption properties. If someone can really come up with such kind of thin film which are optically transparent but microwave wise absorption, nothing like it. But it does have that property.
And any instances or any future what you're thinking, like micro heating based in processing of your sensor materials? Any?
So mostly it's into synthesis, if at all, because our application area is something where probably microwave does not really come directly. But of course, synthesis of materials using microwave is one of the area which I would look. I will try to really look forward to, because this thermal budget, if we can cut down, let's say if we are really talking about translational potential of these devices, uh, we definitely have to talk about the cost of synthesis also. So if you are using very tedious chemical methods or some thermal, requirements are there, that is going to really bring up the cost like anything. So if you can use microwave, nothing like it.
Wonderful, ma'am. Wonderful. Very
Yeah.
nice inputs.
Yeah.
I request other participants if any questions are there, we can post it in the chat box, or we'll just see whether they can be unmuted. We'll just check now.
Yes.
Yeah, we have unmuted the participants. Now, Miss, that restriction has been removed. You can check. If anybody wants to ask question, please ask. Participants, please. We are having another 2-3 minutes. Yeah, you can also use chat box. There are some nice appreciation, ma'am, for you.
Yeah,
Like,
I saw that. Thank you. Thank you. Thank you so much. Yeah.
so if there are no questions, and if any questions comes to your mind later, you can ask madam by emailing her.
Sure.
So I think then if there are no questions, we can end this session, and we can move to the next session.
Sure.
Once again, from the organizing team, we thank you, madam,
Thank you.
for
Thank you for having me.
valuable time and your very important information that you have given to all of us.
Yes. I think there is some question from Yatisha. Yes, please go ahead.
Isha?
Yatisha, any question, please?
I think she has to unmute. Can she unmute?
Yeah, the restriction has been removed. She can unmute. Yatisha? Or Yatisha can at least type in the chat box. We'll get to know that it's by mistake you raise the hand or genuinely want to ask question.
I think some network issue. She has left, I guess.
Okay.
Yeah.
Okay, ma'am. No problem.
Yeah.
Thanks a lot, ma'am.
Satish,
Yeah. Satish. Satish, if you're not able to access, your microphone is still muted, you can use the chat box. I think they'll get back to you, ma'am.
Sure, sure, sure.
Yeah,
I think he's asking something. He's not able to unmute. Yeah. Restriction. Yeah. Okay. Yeah. Now, Satish,
you can
just check. Satish, it is, yeah. Please ask Satish. Restriction. No, now it is blue. No? It should be blue. Then only. No.
Yeah, I think he said that he is going to contact through email. Fine, no problem. No problem.
Hello.
Yeah, please go ahead.
It's unmuted now. Nothing, madam. Just it was a very wonderful presentation, madam. Really.
Thank you.
Just I wanted to know whether you are able to develop the sensors related to healthcare only, or in other field also, like any impact tests or motion, and to calculate the motion or acceleration.
No, so we majorly work on chemical and biological
Okay.
fronts. So we are mostly into this gas sensing for environmental pollutants, or let's say breath analysis sort of thing,
Okay.
or precision agriculture, or these biomolecules. So we could not really enter into this physical parameters yet.
Okay. It's okay, ma'am. Thank you.
I have one question, ma'am, Dr. Ganesh here.
Yes, please.
Like, if we develop some chemical, for example, XYZ for some application, and before using it in the industry, I want to know how much eco-friendly it is. For example, an eco-friendly solution I have developed for. Then, what type of tests I need to do for that chemical? You know, what all gases it will give. Just like for vehicles, we do PUC, right? So, what tests are there specifically, like gas chromatography? What I heard some years back. But
No, gas chromatography is not about it will not give you eco-friendliness or anything. It is a very high throughput and highly sensitive method of getting multiple gases in one shot. So it will not let you know if it is eco-friendly or not. Of course, there is one thing that gas chromatography can do you tell you is, of course, it will not be done by gas chromatography. It can be done by LCMS or some other mass spectrometry, which is going to tell you that if there are any elements in your chemical which is not biodegradable or which is not readily acceptable by the environment. So that test is to be done. There is something called toxicity test. So while handling or let's say degradation of the material should not really generate any kind of any toxic element so that it becomes harmful to the environment. That test has to be done. And if it is, I'm not sure of the application area, because if it is biology, of course, the biocompatibility of the material has to be definitely evaluated. So these tests I'm aware of. I'm not really sure if there are additional tests also which needs to be done.
for example, if I'm developing a cutting fluid, cutting fluid, especially it comes in our mechanical engineering, when we cut the metal, because of friction, there will be tremendous amount of heat is generated and tool life gets compromised. So we use cutting fluids. So if you develop a eco-friendly cutting fluid, and I don't know what all gases it emits at that particular temperature, maybe somewhere around 200 or 300 degrees Celsius. So how can I test that? Like what all gases it generates?
No, that can be done by GCMS. You are right. That can be done by GCMS very nicely. And I think the best way to do it is GCMS only, because if I tell you that optical sensors or IR sensors can tell you these things, then you have to really know what are the gases which are possible over there, and for each of those gases you have to have each individual IR sensor or optical sensor. So that is not feasible. In such case, you are right. GCMS is the only way to go.
Thank you. And do you have GCMS in IIT Dharwad?
No, we do have LCMS, we do have MALDI, we do not have GCMS yet.
Thank you.
Yeah, ma'am. Thanks a lot.
Yeah, thank you.
We'll move to the next session now.
Sure.
Before that, we'll take a bio break of 10 minutes.
10 or 5 minutes?
10 minutes. 10 minutes, and then we'll proceed with the next session.
Yes. So we'll take a break of 10 minutes and then we'll resume from here. We are not signing out from the meeting. We are keeping it as it is. Only recording will be off so that you can start recording for the next session.
Okay.